Humanity has already reached all the planets in the solar system. Rovers are roaming through the red dust of Mars right now as you listen to this. A probe dove straight into Saturn's clouds and kept transmitting as it was destroyed by the pressure. Pluto, the frozen world at the edge of the solar system, has already been photographed from less than 13,000 kilometers away. Crossing billions of kilometers of empty space has almost become routine for us. But there's one direction we've almost never touched. A place that should be the easiest of all to reach, but in practice is one of the most difficult. Straight up out of the flattened plane where all the planets live. Directly above or below the sun, the vertical exit from our own solar system. Sounds simple, right? Point the rocket up and go. The problem is that physics doesn't allow it. What comes next explains why escaping vertically is harder than reaching Pluto. You'll see what's waiting up there if a probe ever makes that journey, and you'll learn about the strange maneuver that scientists are considering now. A maneuver in which the probe first needs to fall toward the sun before it can climb away from it. To understand why vertical escape is so difficult, you need to understand one thing first: the speed you already have right now, without doing absolutely anything. The Earth is in motion, not in a little while right now. Spinning around the sun at about 30 kilometers per second, almost 108,000 kilometers per hour, it's not a translation error. With every passing second, the planet beneath your feet moves 30 kilometers sideways around the sun. In the time it took you to hear this sentence, the Earth has already traveled farther than the distance between Sao Paulo and Rio de Janeiro. And you don't feel anything. No wind, no bump, no sense of movement. Because everything around you is traveling along with you. The air, the buildings, the oceans, the moon. It's the fastest movement of your life, and it's completely invisible to you. Every rocket we launch from Earth inherits this movement. When SpaceX or NASA send a probe into space, it doesn't start from zero. It already takes off flying sideways at 30 kilometers per second, just like you, just like me, just like everything that exists here. Normally, that's a gift. If your destination is out ahead, that sideways push that comes for free does almost all the work. You just need some fine-tuning, a few extra kilometers per second in the right direction, and that's it. You already have a trajectory toward another planet. That's why interplanetary missions are expensive, but possible. We don't build up speed from scratch. We hitch a ride on the speed the planet already has. But what if you want to go up, not toward Mars, not toward Jupiter, not anywhere within the plane, straight up, perpendicular to everything? At that moment, that push that was your ally becomes your enemy. To go up vertically, first you have to cancel out the 30 kilometers per second you already have. Zero it out. Come to a complete stop relative to the sun. And only after that can you add new speed to really go up. The energy calculation is scary. Those who plan space missions measure this with a term called delta V, the change in speed that the spacecraft needs to generate on its own, with its own engines, without anyone's help. Going to Mars, starting from Earth's orbit, costs about 4 kilometers per second of delta V. Leaving the ecliptic plane vertically costs about 30 kilometers per second, almost 10 times more. The worst part isn't even the difference. It's how this calculation works in practice. A rocket doesn't store speed like someone keeps money in their wallet. There is a formula written by the Russian Konstantin Tsiolkovsky back at the very beginning of the 20th century that describes the relationship between fuel and final speed. And its verdict is brutal. Every extra kilometer per second of delta 5 requires more fuel. And more fuel means more weight, which in turn requires even more fuel just to carry that weight. The relationship is not linear. It's exponential. Doubling the delta V doesn't double the size of the tank you need. It multiplies that many times over. That's why nobody just builds a bigger rocket to solve this problem. At some point, the rocket gets so heavy that it can't even lift off from Earth's surface. Math wins before engineering. That's the prison. The Earth's orbital movement gives you free speed in one direction and locks you in all the others. Orbiting the sun? Easy. Jumping from one planet to another within the same plane? Also easy. But the moment you try to leave the plane itself, you have to face 4.6 billion years of accumulated orbital momentum all at once. And here it's worth understanding where this plane comes from. It's not a coincidence or a design choice. When the solar system formed billions of years ago, it was a gigantic cloud of gas and dust slowly spinning. As this cloud collapsed under its own gravity, it spun faster and flattened out, like dough flattening out,
Como massa de pizza.
spinning in someone's hands. Everything that exists today in the solar system was born from that flattened disk, and that's why everything still orbits within it. The plane of the ecliptic is literally a scar from the birth of the solar system, and we're still trapped inside it. It's one of the most counterintuitive facts in all of astrodynamics. Getting to Pluto, more than 5.6 billion kilometers away, takes less energy than reaching a point just a few million kilometers directly above the sun's north pole. For comparison, the escape velocity from the sun itself at Earth's orbit, that is, the speed you would need to leave the entire solar system for good, is about 42 kilometers per second. And look how interesting that is. Leaving vertically from the plane of the planets at just a few million kilometers high already costs almost as much as that. It's practically the same price as leaving the solar system forever. And that's why there's a huge list of places humanity has already visited and a very short list of missions that have tried to leave the plane. It's not a lack of interest. It's not a lack of camera technology or scientific instruments. It's the energy bill, plain and simple, blocking the way. Since leaving the plane vertically is so expensive, almost no probe has ever made that journey. And that means one thing. Pretty much everything that happens directly above or below the sun, even in 2026, is still a frontier. We have detailed maps of Mars, high-resolution photographs of Pluto. We can show close-up images of comets, asteroids, Saturn's rings, and Jupiter's moons. We've already landed on Titan. We've already brought asteroid samples back to Earth. We've already photographed the black hole at the center of our galaxy. But the poles of our own star, the closest one there is, have barely been seen. And that matters much more than it seems. The polar regions of the sun are where the most violent and most important solar activity actually happens. That's where the fastest solar winds come from. That's where the sun's magnetic field starts to reverse every 11 years in a process that no one fully understands yet. Think about that for a second. Every 11 years, the entire magnetic field of our star flips upside down. Magnetic north becomes south. South becomes north. A star with more than 1,000,000 times the volume of Earth simply switches polarity and then switches back. And the trigger for this whole process is precisely in the regions we've never been able to observe properly. All the space weather in the solar system is shaped by what happens above and below the equator of our star. And we've been observing this almost entirely from the side. It's like trying to understand the climate of an entire planet while standing only on the equator, never being able to look at the poles. And space weather is not an abstract subject. In March 1989, a geomagnetic storm knocked out the entire power grid of the Canadian province of Quebec. 6 million people were left without power in the middle of winter. In 1859, a much larger event, now known as the Carrington event, caused telegraph systems to catch fire and auroras to appear near the equator. If an event of that size happened today, with our dependence on satellites, GPS, and interconnected power grids, the damage would be counted in trillions. Predicting this in advance depends on understanding the sun's magnetic field. And understanding the sun's magnetic field depends, in large part, on being able to see its poles.
Only 2 missions have come close to a real polar view of the sun in the entire history of space exploration. The first was Ulysses, launched in 1990 in a partnership between NASA and the European Space Agency. And the way it solved the delta V problem was, to say the least, creative.
Since there wasn't a rocket capable of pushing the probe straight up, the engineers did the opposite of what intuition would suggest. They sent Ulysses in the wrong direction. It first traveled outward toward Jupiter, the gas giant, the most massive object in the solar system after the sun itself. Once there, it used the planet's immense gravity as a slingshot, curving its own trajectory by almost 80 degrees out of the plane of the planets. Only then did it fall back toward the sun in a completely tilted orbit. In other words, to go up, Ulysses first had to cross half the solar system in the opposite direction and borrow the gravity of another world. Without Jupiter, that mission simply wouldn't have been possible with the technology of the time. Maybe not even with today's tech. And it worked. Ulysses spent almost 2 decades in operation and brought the first direct measurements of the fast solar wind coming out of the polar coronal holes. It discovered that the sun is, in terms of solar wind, 2 completely different places. Near the equator, turbulent and chaotic, and another near the poles, fast and more organized. But there's a huge frustration hidden in this story. Ulysses was built with instruments designed in the 1980s. It didn't have any camera capable of photographing the poles. The probe got up there, measured particles, measured magnetic fields, sent back valuable data, and didn't bring a single image. And we learned about the conditions of that place, but we never actually got to see it. The second mission is happening right now, while you're watching this. The Solar Orbiter, a probe from the European Space Agency launched in 2020, took a different and much more patient approach. Instead of a single giant slingshot at Jupiter, it's been using repeated flybys of Venus, each one tilting its orbit just a little bit more. It's a slow process, made up of orbit after orbit, like someone climbing a spiral staircase instead of trying to jump straight to the next floor. And it worked. In March 2025, the Solar Orbiter sent to Earth the first direct images of the sun's south pole ever recorded in human history. And what appeared in them surprised even those who were expecting them. A chaotic region with the magnetic field all tangled up, with north and south polarities mixed together in the same place. Nothing like the organized solar surface we see from here, face on. But it's important to be precise about the size of this achievement because it's smaller than it seems. The Solar Orbiter isn't hovering over the sun's pole, looking down from above, like a weather satellite looks at Earth. It's tilted. It sees the poles at a slant, at an oblique angle, which improves only a little with each orbit it makes. It's the difference between finally being able to peek at your house's roof from a side window and actually flying over it. Even after years of maneuvers with Venus, the maximum angle it will reach is still far from a true polar view. In other words, even the most successful mission in history on this subject still hasn't solved the problem. It only proved how big it is. Stop and think. Think about that. Until last year, no human, no robot, no camera had actually seen what the top or the base of our sun looks like. Not from above. The closest and brightest object in our local universe, the only reason life exists here, and there are still 2 entire regions of it that have only just started to be photographed now. And it's worth making a note here because there's a probe that proves that getting close to the sun, at least from the front, is no longer science fiction. NASA's Parker Solar Probe broke the record for the fastest object ever built by humanity, 692,000 kilometers per hour, which is equivalent to 192 kilometers per second, during a pass just 6.1 million kilometers from the surface of the sun in December 2024. At that speed, you could cross the entire length of Brazil from north to south in about 20 seconds. And the probe survives protected by a carbon fiber heat shield that's just over 11 centimeters thick, with the side facing the sun reaching nearly 1,370 degrees Celsius, while the body of the spacecraft right behind it stays at a temperature close to that of a room. It got there after 7 gravity assist maneuvers at Venus over several years, each one tightening the orbit a little more. This shows something important. The engineering to survive near the sun already exists, has already been tested, has already been proven, and has already broken records. That's not the part that's missing. What's missing is reorienting the entire trajectory upward. And there's a second reason why vertical escape matters so much, maybe even more profound than the issue of the sun's poles. We don't even really know what our own solar system looks like from the outside. Around the sun, there's a gigantic bubble called the heliosphere. It's the region where the solar wind dominates, pushing back the interstellar medium that exists beyond it. Inside it live the planets, the comets, the Kuiper Belt, and every probe humanity has ever launched. Outside, the deep galactic environment begins, full of cosmic rays and interstellar particles from which this bubble silently protects us all the time, since before life existed on Earth. The scale of this thing is hard to grasp. The edge of the heliosphere is more than 100 times the distance between the Earth and the Sun. Sunlight, which gets here in 8 minutes, takes about 17 hours to reach that boundary. It's the largest structure our star creates, and it's literally humanity's address within the galaxy. For decades, we assumed that the heliosphere had a comet-like shape, a rounded front colliding with the interstellar wind in the direction of our movement through the galaxy, and a long tail trailing behind. It was the classic textbook image, the one that appeared in every museum illustration and every documentary. A good guess, considering the data that existed at the time. But in 2020, a team led by the scientist Merav Ofer from Boston University, using a new model based on NASA data, came to a very different conclusion. The heliosphere probably doesn't have a comet shape at all. The new prediction looks much more like a wilted croissant, with a curved central bulge and 2 short jets curling outward. And the most surprising thing of all, no long tail at all. Notice the size of this change. It's not a minor adjustment, it's not a 2% correction. It's the difference between thinking you live in a house and finding out you live on a boat. The entire structure that encompasses everything humanity has ever known might have a completely different form from what appears in all the books. The reason we still don't know for sure is simple and not very unsettling. We've never seen our bubble from the outside. The Voyager probes cross the heliopause sideways, almost within the same plane as the planets. Voyager 1 in August 2012, Voyager 2 in November 2018. It was a historic achievement, the only human-made objects to cross that boundary. But the 2 crossing points are almost on the same plane. They confirm that the bubble exists and measured what it's like at that specific point. They don't reveal its overall shape. It's like trying to figure out the shape of a dark room by only being able to touch 2 points on the wall. You prove that the wall exists, you measure its texture, but you have no idea if the room is square, round, or shaped like a deflated croissant. And how little we still understand about this frontier becomes clear in another real example. In 2009, a NASA probe called IBEX, much smaller and cheaper than the Voyagers, made the first complete map of the entire sky using energetic neutral atoms coming from the edge of the heliosphere. It's an ingenious technique. Since that frontier doesn't emit visible light, it's impossible to photograph it with a regular telescope. But particles that bounce from there come back here and work as a kind of fingerprint of the place they came from. And the map revealed something that no model had predicted: a narrow ribbon-shaped band crossing the entire sky, emitting far more particles than anything around it. No one expected it. No simulation had predicted that. To this day, more than 15 years later, no one is absolutely sure what causes this ibex ribbon. The most widely accepted theories link the phenomenon to the way the galaxy's magnetic field meets the solar wind right at the edge of the bubble. But it's still just a theory. We haven't even finished properly mapping the boundary of our own cosmic home. And here's an important update about this gap. The mission designed specifically to tackle this problem is no longer just a project on paper. IMAP, NASA's Interstellar Mapping and Acceleration Probe, was launched in September 2025. It reached its observation point, Lagrange 1, about 1.5 million kilometers from Earth in the direction of the Sun at the beginning of 2026, and has already started its main scientific mission. Right now, it is using 10 different instruments to map the boundaries of the heliosphere from the inside out with much greater sensitivity than IBEX. But even with IMAP operating at full capacity, it is still a probe looking out from the inside, not a probe looking down from above. For a direct and definitive view of the real shape of this structure, the only way remains the same: escape vertically and look back. A vantage point that no probe has ever reached, to reveal the shape of the place where we live without ever having seen it from the outside. So, how do we solve the problem of vertical escape in practice? We've already seen that we can't just build a bigger rocket. The math of fuel doesn't allow it, and Jupiter isn't always in the right place to lend us its gravity. There's a counterintuitive solution that's been discussed in space mission design circles for years, and now it's moving from theory to concrete proposals. It's called the Solar Oberth Maneuver. The idea works backwards compared to the normal way of piloting a rocket. Instead of pointing the engines upward and trying to go up right away, you do the opposite. You let the spacecraft fall toward the sun. You let it dive inward, accelerating under the sun's gravity, gaining speed with every kilometer traveled, until at the closest point, it's moving at hundreds of kilometers per second, possibly more than 100 kilometers per second. At perihelion, in the same speed range as the Parker Solar Probe, it has already been shown to be survivable. And it's exactly at that moment, at the point of highest speed and greatest danger of the entire mission, that you fire the engines. Why? Because of a principle that the scientist Hermann Olbert described in 1929, long before any rocket had left the atmosphere. A rocket burn is much more efficient when done at high speed inside a deep gravitational well. The same amount of fuel generates a much greater gain in orbital energy at perihelion than it would at any other point in empty space. It's not magic, it's the geometry of energy. Kinetic energy doesn't increase in proportion to velocity. It increases with the square of speed. And that means when you're already going really fast, each small increase in speed is worth much more in total energy than it would be if you were going slowly. Burning fuel while standing still in the middle of nowhere is a waste. Burning fuel at the bottom of the sun's gravitational well at 100 km/s is taking advantage of a huge amount of energy that gravity has already put there for free. By firing the engines right at the point of closest approach, you get a Stirling effect without needing another planet for it. The fuel that came all the way from Earth turns into much more kinetic energy than it would anywhere else along the journey. The sun itself becomes your booster. After the burn, the spacecraft is going so fast in such a useful direction that it finally manages to climb out of the plane and head straight toward the solar poles, or out of the solar system for good, faster than any probe ever built. The dive becomes the launch pad itself. Of course, there's a price. Executing this maneuver means putting a spacecraft in the hottest and most hostile region of the solar system exactly at the moment when it needs to fire its engines with almost perfect precision. An error of just a few seconds in the ignition wastes much of the gain. A poorly oriented heat shield means losing the entire mission. It's extremely high-precision engineering, carried out millions of kilometers away. Too far away for any correction to arrive from Earth in time. Solar sails also come into this conversation by a complex path.
Completely.
Opposite concepts like the one proposed.
Solar Polar Imager and the most recent high-inclination solar mission.
They depend on huge reflective sails that use the pressure of sunlight itself to gradually tilt a probe's orbit. With no fuel at all, just photons pushing a thin metallic film spread over thousands of square meters. And this isn't science fiction. Japan tested the principle in interplanetary space in 2010 with the Icarus probe, which sailed toward Venus propelled by sunlight. The Planetary Society proved that the technology works in Earth's orbit with LightSail, 2 in 2019, changing its own orbit using nothing but solar radiation. The pressure exerted by light is ridiculously small, comparable to the weight of a paperclip spread over a sail the size of a city block. But it never stops. It works 24 hours a day, every day, for years on end. And that's where the beauty of it lies. Solar sails.
They take years,
To spiral up to a polar orbit.
but they don't need any propellant. The longer they push, the greater the inclination they achieve. A fuel-powered probe has a strict limit. When the tank runs out, that's it.
A solar sail only stops accelerating when the sun goes out, as long as it stays in our skies.
To pull off that feat,
Designed exactly to prove this capability in practice. It was called Solar Cruiser. A solar sail of more than 1,650 square meters, almost the size of a soccer field. Specifically designed as a technological pathfinder for future missions, capable of tilting its orbit to achieve a polar view of the sun. The idea was to launch it as a secondary payload, along with IMAP itself. The project made significant progress in development before being canceled due to budget and scheduling issues. But even without ever taking off, it made one thing clear. Within NASA itself, going vertically up to the solar poles is no longer just an academic curiosity. It became a serious engineering goal, with funding, a team, and a schedule. The will exists. All that's missing is someone to see it through to the end. Now put the two ideas together. A probe that uses a solar sail to spiral closer and closer to the sun. It performs an Oberth maneuver right at perihelion to redirect itself vertically. And it keeps being pushed by the sail until it reaches the polar regions. Patience and violence in the same mission. It's this kind of architecture that astrodynamicists today believe can finally give us a clear view of what's above and below our star. If that ever really happens, what exactly would a probe see directly above the sun? First, the view itself physically changes. The ecliptic plane is dusty. The Earth, like every planet, passes through a thin haze of dust left by billions of years of comets breaking apart, asteroids colliding, and the slow wear and tear of the entire solar system. We live inside a cloud of debris and don't even notice. And you've already seen this dust with your own eyes, even without knowing what you were seeing. On a very dark night, far from any city, right after sunset or just before sunrise, a faint pyramid-shaped glow rises from the horizon. It's called zodiacal light. Many people mistake it for the glow of a distant city. It's not. It's sunlight reflecting off the dust in our own plane, the inner solar system illuminated right in front of you. A probe that went above the ecliptic would leave that dust behind in a matter of months, and the view up there would be dramatic, much clearer. Less scattered light, less background noise. Exactly the kind of place where a telescope would be able to pick up faint signals that, here inside the disk, are completely drowned out by the surrounding dust. This has a huge consequence. One of the biggest obstacles to detecting Earth-like planets around other stars is precisely the noise. Signals that are too weak, lost in the background brightness. An observatory installed well above the plane of the ecliptic would be one of the best possible spots in the solar system to search for signs of life on other worlds. And from the same place, a different instrument could measure the cosmic background radiation, the echo of the Big Bang itself, or study the structure of the plane of our galaxy as seen from outside it. Second, the solar environment changes completely. Above the sun's equator, the slow solar wind, about 400 kilometers of turbulent and irregular plasma, full of gusts, gives way to something much more stable. Above the polar coronal holes, there is a stream of fast solar wind between 700 and 800 kilometers per second of particles flowing outward in a thinner and much smoother stream.
A probe crossing this stream would face a fundamentally different radiation environment, with direct consequences both for the lifespan of its electronics and for the science it would be able to conduct there. And, more importantly, it would be the first time we would measure this stream with modern instruments, with cameras, with the technology that Ulysses didn't have in the 1990s.
And third, the big picture. From an observation point well above the ecliptic, the solar system itself would finally become visible as the flattened disk it truly is. You would see the planets lined up in their flat ring around the sun, with dust clinging to the central plane and the heliosphere surrounding it. All of this in whatever real shape it actually has, whether it's a comet, a croissant, or anything else that no one has imagined yet. We would be able to look at our own neighborhood for the first time, just like we look at Earth from orbit today. And it's worth remembering what happened the last time humanity got a perspective like that. In 1968, when the crew of Apollo 8 photographed the Earth rising behind the lunar horizon, that single image changed the way billions of people saw their own planet. It wasn't new science. Everyone already knew that the Earth was round and small, but seeing it from the outside with their own eyes was different from just knowing it. We've never seen the equivalent view of our solar system. No human, no robot has ever sent that photograph back. Of all the images we've ever managed to capture of the cosmos, from galaxies billions of light years away to supermassive black holes to the first lights of the universe, this one looking down at our own solar system, seen from outside its plane, is still missing. It's the closest to home photo that humanity has never taken. And for now, all we have in its place are illustrations, drawings made by artists based on mathematical models, showing what the solar system probably looks like from above. Every image you've ever seen of the entire solar system, in every book, in every documentary, in every animation, is this, a well-informed guess. None of them is a photograph. And maybe the most uncomfortable detail of this whole story is this. What separates humanity from this image is no longer a scientific mystery. The physics is settled. The maneuver is described. The materials exist. The heat shield has already been tested under real conditions. The solar sail has already sailed through interplanetary space. No one needs to invent anything new for this mission to happen. What is missing is a decision. Budget approved, timeline justified. A space agency willing to fund a journey that takes years to yield results and doesn't end in any landing, any flag, any footprint. Only in a photograph, the strangest and most familiar of all possible photographs.